Okay, so I'm not sure why PowerPoint doesn't want to make this bigger, but whatever. My name's Ryan. I represent CONEXUS AI. I'm going to start by just describing what we are. We have software that you can go download. I'm going to give a demo of that. And then I have a special announcement as well. So get started quickly. So who are we at?
Slides full screen so we can read.
These, I'm sorry, say again?
Hit full screen.
I'm trying, but like this view button doesn't work. F5?
Alt F4.
Ah, I'm impressed you knew the shortcut. Yeah, okay. Right, so we are a startup spun out of AI in it. So there's a long story behind the name. But the basic business model here is to take that work on categorical databases, and since it's better because of category theory than all the stuff out there now that manipulates data, such as SQL, try to productize it. And so the thesis here is that there's actually a large market for this because we have more data than ever and people trying to do things like apply AI to it. And you can't really do that without migrating, integrating, cleaning data. And our technology does that quite well. So that's the basic business idea. We got SBIR funding initially from NIST, from Sub, Spencer, those folks to spin this thing out of MIT. So those are, they're grants in the US, but they're designed as technology transfer grants to allow labs such as ours to function while we're in a state where VCs may not, where we might be still too risky for VCs. So that went really well. We used that funding to solve research challenges, and since that worked, now we're privately funded, doing pilot projects, have some revenue, and there's a community that's developed around what we're doing. So Christina's an advisor. Josh, who's doing his PhD here, was an intern of ours for a while. We are down at NIST a lot. There's even some users of the tool I'm about to show, which is called CQL, such as Zan's. He's been a participant on our email list. So the bulk of this talk is going to be just a demo of the technology we have, but I am going to skip to the end of this talk to give the announcement first, because I think this is the probably more exciting part for the folks in this room. So that is, we have, as part of our commercialization efforts, Silicon Valley style commercialization efforts, funding available to other startups with good business plans and connections to our intellectual property to try and get this algebraic or categorical approach to databases out into the world, as well as the related things that came out of 7 sketches and stuff like that. So we have what's called an RFP. This is a request for proposal posted to our website there. It's closing soon, but yeah, anyway, don't hesitate to contact us if you have questions about that. But we're also soliciting applications from people because what we're finding is that startups will apply. They don't necessarily have all their personnel needs in place. There's also just individuals in this community who are kind of isolated but want to work on applying category theory. And so we're trying to match people up as well as look for people who might want to come work for us directly. So anyway, this funding's available. It is in exchange for equity, so these are not grants. And you got to have a good business plan. But if you have all those things checked off, we can get you a check next week. So anyway, that's the surprise announcement.
That was a joke.
No joke. But if you don't have a good business plan, don't expect a check. So, right. Okay, so with that, what I'm going to do with the time remaining is first just walk through some slides on what our software does and then actually show it. So the slides, they're available at that URL. I also, do you think Control F5 will work here too? Maybe not. Is this still good enough if I just show this slide here on the web browser like this?
There's a features page button, and you press F11 to go to full screen.
F11. Ah, wow. Oh, fit to page. Oops, I'm back. There we go. Right. So the tool I'm about to show, it works with essentially finitely presented categories and co-presheaves over them. So hopefully this diagram will be very quick to explain for the folks in this room. Basically, you have here on the upper half of the line a presentation of a category. It has 3 objects: employees, department, and strings, and then 6 generating arrows here marked as the edges in that graph. Each employee has a manager, each employee works in a department, departments have secretaries, employees and departments have names. Plus, you have the equation part of the presentation, which is this here. So these are written in kind of a stylized syntax, but basically it says that if you, this one for example, says if you start at manager, or you start an employee, you find their manager, you find where they work in, that should be the same as just where that employee works in, right? So these are just the equational part of a category presentation. Down below it is a co-presheaf on that category, so a functor to the category of sets. So there are, the set associated with employee has 3 elements, 101, 102, 103. Those are your employees. That's this column here. Each of these edges corresponds to a column in this table. So this has been kind of a recurring theme at this workshop. But anyway, the point here is that these co-presheaves are tables that look like they come out of a database, right? And up at top you have what looks like a schema. And we're not the first people to observe this, but we've been building up a tool around it based on this kind of understanding. So I'm going to go ahead and switch to the tool, but let me pause here and take questions. Okay, cool. Actually, I'll do one more slide before, 2 more slides before getting to the tool, which is, so here we have a category and a co-presheaf, right? But that's enough to say what your data is, but we really want to move data around, right? So the way in which this tool moves data around was, this was David and some other folks' original observation, was that because we think of database schemas as categories and database instances as presheaves, you can use change of basis functors to move data around. So for example, suppose you have 2 finitely presented categories S and T, which you think of as schemas, and a functor between them. If you have a database on the schema of the target of your functor, you can compose with your functor and get a schema or a database instance on your source schema. So this is just composition. And then there are adjoints to this operation here, which we use to move data around. And it turns out that these adjoints, pi and sigma, correspond roughly to database joins and database cojoins, which do not actually exist yet, but exist in our tool. And that's one of the value propositions, is that some of these operations coming from category theory have just never been seen before in a context of data management. So with that in mind, I'm going to bring up the tool. If I can get back out of here. Oh. There we go. All right, so here's the tool. And I'm going to give some more categorical types of examples than data management-y ones, since that's the audience here. So how's that to view? Bigger still? Oh yeah, full screen. So I thought I'd start by demonstrating the automated theorem proving of this tool. So it turns out if you have just 2 finitely presented categories in an assignment between them that you want to think of as a functor, even checking that that assignment is functorial is undecidable. So right from the very beginning, to use category theory as a language to manipulate data, you have to deal with undecidable problems. And we've chosen to do so using techniques from automated theorem proving. So think of this schema here as just a category. It has one object M, one generating arrow F, which is a non-trivial endomorphism subjects to these equations that 3 times through F is the same as 2. We're going to try to map that, create a functor from that to another category, finitely presented category. One object, one generating arrow, different set of equations. So this one says 4 times through with f should be the same as 3 times through with f. So you can inject t, or you can map from t to s just like this. This is an inclusion, I think, or a mono or something. Anyway, the point is it's a legitimate functor if you map the m of one to the f of another. So is this mapping here, where you take the one object of s and map it to the one object of t, and the one generating arrow and map it to a composition of 2 arrows. But here is an assignment that doesn't work, right? So there isn't, this assignment here, to M, F to F, if we're going from category S to category T, is not functorial. It's just not a functor. And so this tool here uses automated theorem proving techniques to actually rule that out at compile time. And so you get really strong notions of static correctness out of this tool. And I'd like to think, just as a use in category theory, that maybe in your day jobs you have to check that things are functors from time to time. Maybe not. What's that?
Or a computer left cone extension or a right cone extension.
Right. So as David pointed out, this thing does a lot more than just check if things are functors. It's designed to take over the universe. So here's an example of some actual data and the like. So one reason we use words like schema instead of category and instance instead of co-presheaf and all of that is that there's a lot more here that is kind of related to databases than category theory per se. One example of this is that in a database context, you typically have what you might think of as infinite sets, strings, nats, and you have that in addition to the data that you're thinking about, your employees, your departments. And so to get all the theory to work out, there's some math to do, which has been written up in several hundred pages worth of papers at this point. Anyway, since I'm getting close to the 15 minutes, I'll just show you what this stuff looks like in the viewer. So here is our little schema for employees and departments that I briefly mentioned in the talk. Here is a set valued co-presheaf on it. So same kind of tables, right? Here's the CS department, the math department. Here's your 3 employees, Carl, Al, Bob. So you can get data into this thing. You can map between schemas, like I was showing earlier. Use change of basis functors to take an instance that looks something like this on one table and split it up into, oh, that's not the right one. I wouldn't think. Here we go. Yep, split it up into 2 tables with, in this case, unknown first names, so you can use it to change schemas of things. We've been doing projects to do data integration, so here's a built-in example that does co-limits of co-presheaves and also co-limits of finitely presented categories in the service of data integration. And it's designed to be feature parity with other tools in its class. So yeah, we are encouraging people to go use it. You can download it. It's at categoricaldata.net. The version you see here, it's open source, GPL license. It runs gigabytes of data on a single node. If you want something that runs like petabytes of data on your Spark cluster, that's the proprietary version. But the open source one that you could even contribute to if you wanted, it's a GPL license, is available for free and more than sufficient for most work. And there's a ton of papers and case studies and stuff in our website. So thanks. Questions?
So I was interested in these theorem proving techniques that you use. How does that work? What do you use?
It works with much effort. So it uses a few different theorem provers depending on the syntactic form of the theory you give it. We are fortunate that at least for presentations of categories, if you don't think of products, co-products, that kind of thing, that those are what automated theorem proving people would call monoidal. You have this structure where there's no, everything has arity 1. And so there are special techniques that apply to that case that we have really, really fine-tuned over the years. And so in fact, this theorem prover, that particular prover I'm talking about, will decide any theory in that form that admits a non-length increasing equivalent rewrite system. So it's pretty expansive. The issues come more when you step out of that fragment and try to do things like addition, or it's easy to get undecidability. You can put the SKI combinator calculus in here very easily, and then things start to break.
What about constraints? If I want to replicate the schema, some constraints, what type do you use?
Right. So in addition to the equations that you get out of just the presentation of the category, we've added what are called, the database people called, or continue to call, embedded dependencies. Logicians or other people call them things like finite limit logic, or regular logic even. But basically what you do is you write your schema as before, but instead of equations, you just write little first order logic-y things, right? This says that a nose relation encoded as a span of 2 functions is symmetric, and it just looks like logic. And we have a bunch of theorems about how this relates to the relational first, and all of that. So.
Do you have plans to extend beyond this type of constraints?
We definitely want to get disjunction in here, but after that, the next step is like all of first order logic, and at that point, things become really untractable. I think more important is like a GUI, a user interface, to allow people to manipulate these constraints, kind of along the lines we saw earlier, or at another talk. Yeah. Other questions?
You said something about scale already, gigabytes and petabytes.
Yes.
But what's the scale of what you actually use it on?
What do the scale of what people usually use this for? It depends. Mathematicians just use the schemas without any data, right? So it doesn't get any easier than that. Whereas we go to computational chemists and they just expect it to be able to accept, 100 gigabytes of data out of the box. So in practice, we're seeing things at like the less than 10 gigabyte level, and it's not having any trouble with those. But we know that people want to scale it up further. Yeah.
And forgive me asking, but for customers or people who are paying, or for
Yeah, even people who are buying, right? Like a lot of data out there isn't big, and if you already have like a massive Spark cluster or something, you're like in a different class of user already. So this is designed to deploy. So as opposed to execute on the local node, it's designed to generate code and then go off and run that way. So yeah. Question next to you.
So do you have customers already?
Yeah, we have revenue. In fact, just this week we signed a paid pilot project with a group of farmers here in the UK, led by Freeman Dyson for some reason. So I don't, who knows? It's like, but I guess he's big into technology and is also a farmer or something. So yeah. Also, you may be interested to know this with Professor Rosebeb's permission. We've taken over maintenance of ESIC. So. In principle, you can move to the extent that the sketches formalism, the EA sketches, is compatible with REDs, their embedded dependencies. You can move back and forth between the two tools seamlessly. Yeah. So it also helps with our GUI because you guys did a good job with your reactor.
I think we sort of have to move on now a little bit.
I have one more question. How do you manage nulls?
Sorry?
Nulls.
Nu-
Nulls.
Nulls. Oh,
Unknown value.
labeled nulls.